Okay, we're going to go over some more examples. We're going to review the ratio and the root test. So we have n to the 10th power here over negative 10 to the n plus 1. So this is an. An n to the 10th over negative 10 to the n plus 1 power. So looking at the next term, replace n with n plus 1, we'll get n plus 1 here. And so let's look at the absolute value of the ratio of the two terms, meaning an plus 1 over an, n plus 1 to the 10th power over negative 10 to the n plus 2. We're going to save some time and multiply by the reciprocal here. Negative 10 to the n plus 1 over n to the 10th power here. Now, we're going to look at this in absolute value again. So this is where we're going to use the algebra that we've been talking about here. And let's see what we get now. So this is the absolute value. N plus 1 to the 10th power over negative 10 to the nth power times negative 10 squared. Okay. Negative 10 to the nth power times negative 10 n to the 10th power. Just using properties of exponents. Now cancellation here and here. So we're going to have now the absolute value of n plus 1 to the 10th power over negative 10 times n to the 10th power. So down here, we're going to use properties of absolute value to pull out that denominator. We're really going to get 1 over the absolute value of negative 10. And again, by properties, n to the 10th power here. This is really just 10. And what you have here, again, is going to be strictly positive now. So, all right. So we really have 1 over 10 times n plus 1 to the 10th power over n to the 10th power. And I guess we can still use some algebra. So let's go back to our purple. 1/10 n plus 1 to the 10th power over n to the 10th power means we're going to end up with one over 10 n plus 1 to the nth power, or n plus 1 over n to the 10th power here now. All right, this is the absolute value of the ratio. So as we take the limit, an plus 1 over an, that's really the limit of 1/10, 1 plus 1 over n to the 10th power. So we can factor out the constant or pull out the constant by properties of limits. And we know this limit goes to 1. And 1/10 times 1 equals 1/10, which is strictly smaller than 1. This is what we're looking for. That means the series converges absolutely by the ratio test. Now, absolute convergence implies convergence here. So we can end up saying here that this particular series converges by the ratio test. And this is what we mean. Being less than infinity means the sum is finite. So converges by the ratio test. Number 6. All right. Number 7. You might be tempted to say the root test, but it's not the root test because you don't have a base to the nth power to apply the root test. This numerator here, as n factorial, does not involve an nth power here. So we're going to use the ratio test. All right. An is n factorial over nth to the nth power. So that the next term, replace n with n plus 1, is n plus 1 factorial over n plus 1 raised to the n plus 1 power. So an plus 1 over an is n plus 1 factorial over n plus 1 to the n plus 1 power times n to the n over n factorial here. Don't forget, we need to take this in absolute value now. All right, use again algebra here. All right, some algebra. Now, the definition of n plus 1 factorial we can write as n plus 1 times n factorial. That's multiplied to n over n, and then properties of exponents, n plus 1 to the n times really n plus 1 to the first power. And that's over n factorial in absolute value. So just use the cancellation property now, and the fact that everything you have between the absolute value sign is positive, which means you're left with n over n plus 1 to the n. Now, by properties of exponentials, that's a over b to the n. This is, again, some of the algebra that we use. So you have n over n plus 1, and that's going to be to the nth power. Let's write that nicer, I guess. Right? So n to the n over n plus 1 to the nth power. That's not much nicer. All right. It's a little better. All right. So the limit of the absolute value of the ratio turns out to be the limit of n over n plus 1 to the nth power. Now, this is as n goes to infinity. Now, this is going to turn out to be 1. Here's what I'm saying. The limit as n goes to infinity of n over n plus 1 is 1. So you're looking at 1 to the infinity power here. Now, if we go back to calculus, looking at this particular limit, x over x plus 1 to the x power, this is where we have an indeterminate power. It's really calculus 2. So where we're headed with this is to use L'Hopital's rule. So we have to go through the process where we let y be x over x plus 1. So natural log y, and let's go back here. Get the natural log x over x plus 1 to the x power, which means we'll say natural log of y is x times the natural log of this difference here. So let's recall, as x goes to infinity, what happens on this right side here? We get infinity times 0, an indeterminate product. We have to fix this. So I'm going to write this as, keep the natural log in the numerator. Natural log of x over x plus 1 over x. Yeah, let's double check. This goes to infinity. Yeah, times 0. We didn't fix this. That's what the problem is. 1 over x. Let's remember this is called the fix. It's an algebra fix, so I'm going to color that purple. There we go. Now the limit is 0 over 0, an indeterminate quotient now. So let me kind of continue with some properties here after we fix this. This is the natural log of x minus the natural log of x plus 1 by properties of logs over 1 over x, so that when we apply the L'Hopital's rule here now, we get 1 over x minus 1 over x plus 1 over, I believe it's negative 1 over x squared. All right. So using some algebra now, guess we have to go back to purple. This is going to be, instead of dividing by a fraction, we multiply by negative x squared. So we get negative x squared over x minus x squared over x plus 1, which is negative x minus x squared over x plus 1. All right. So what this means is the natural log of y is negative x minus x squared over x plus 1. So let's see what happens to the limit. As x goes to infinity, we know negative x goes to minus infinity, and we know that, we'll look at the second term, negative x squared over x plus 1. This is going to go to minus infinity as well. So what we're seeing is negative x minus x squared over x plus 1 goes to negative infinity here. All right. So the natural log of y goes to negative infinity. So e to the natural log of y goes to e to the minus infinity, which really means 0. Y is going to 0 here. Oh, let me go back and double check here. Exponential function. Yeah. e to the x, x is going to minus infinity. Yes, y goes to 0. So what did we just see here? Essentially, this limit equals 0. Let's double check. And that 0 is less than 1, by the way. So this is smaller than 1. And that's what we're looking for. Because by the ratio test, we have absolute convergence, which implies we have convergence here. This converges by the ratio test. All right. Okay. 2n factorial over n factorial squared here. All right, we're going to have to use the ratio test again. So an is 2n factorial over n factorial to the second power, which means an plus 1 is 2 n plus 1 factorial over n plus 1 factorial now to the second power. All right. Looking at the ratio now, I'm going to do a little algebra here. We get 2n plus 2 factorial over n plus 1 factorial to the second power. This will be times now the reciprocal, which is n factorial squared over 2n factorial. Okay. Got to take the absolute value here. So right in here, we're going to use again some algebra. All right. So 2n plus 2 factorial. Remember the definition. I know right up here, I have a 2n factorial in the denominator. So I'm going to stop. We have 2n plus 2, 2n plus 1, and then I'm going to say 2n factorial. I got n factorial squared, so my numerator is taken care of here. But I have n plus 1 factorial to the second power times 2n in parentheses, or 2n factorial. Okay. So let's see what's going on here at least. We could get rid of, by cancellation here, 2n factorial. Now I'm going to focus on n factorial squared and n plus 1 factorial squared. I'm going to use the same idea here. So in absolute value, 2n plus 2 times 2n plus 1, n factorial times n factorial over, this portion here is n plus 1 factorial times another n plus 1 factorial. So I'm going to write it as n plus 1 n factorial and then another n plus 1 n factorial down there. in absolute value here. So what you'll see with cancellation is the same thing. We're now left with the absolute value of 2n plus 2 times 2n plus 1 over n plus 1 times n plus 1 in absolute value. All right. Okay. So these terms are all positive now. Everything within the absolute value is now positive, so we can get rid of the absolute value. And when we do that, we end up with 2n plus 2, 2n plus 1 over n plus 1 times n plus 1. All right, now this is the ratio that we're looking for. We're going to have to take the limit now as n goes to infinity, the absolute value of an plus 1 over an plus 1, which is the limit of 2n plus 2, 2n plus 1 over n plus 1 times n plus 1. Now, let's write this a little better. So, I mean, I think we could use, again, some algebra here. Okay, we're going to put that down as using some algebra. And this would be the limit now of, we're going to have to use FOIL on top and bottom. Okay. 4n squared plus 6n plus 1 over n squared plus 2n plus 1, a calculus 1 limit question. And this limit's going to equal 4. And that is strictly bigger than 1. So because 4 is bigger than 1, we got divergence now. So this series diverges by the ratio test. All right. Okay, let's look at number 9 and see what happens here. Again, you may have an n squared term up here, but we can't use the root test. It's a ratio test. an 2 to the n squared power over n factorial. The next term, an plus 1, is 2 to the n plus 1 squared over n plus 1 factorial. So, looking at the ratio, we get 2 n plus 1 squared over n plus 1 factorial times n factorial over 2 n squared. We need to see what happens with this by using some algebra. Okay. All right, the algebra now is 2 raised to the n plus 1 squared power times n factorial over n plus 1 times n factorial. Then that's 2 to the n squared power here. So it looks like all we can do for now is get rid of the factorials. And then everything here under or in the absolute value sign, is positive. So this is really going to be 2 n plus 1 squared over n plus 1, 2 to the n squared power here. But, all right, I hate that. But we're going to use some properties here. Okay, it's more algebra essentially here. So what we have now, I'll get out the purple, it'll be 2 to the n plus 1 squared minus n squared power over n plus 1 by using some more algebra. You're using essentially the following, you say a to the n over the same base to the m power, that's a to the n minus m. Beginning algebra, properties of exponents here. Okay? So now here, we'll use some FOIL. Or actually, yeah, FOIL for this n plus 1 squared term, and then we're going to subtract here. Okay? So n plus 1 squared, all right. Two n squared plus 2n plus 1 minus n squared over n plus 1 now. So you're going to get 2n plus 1 over n plus 1. All right, so let's take the limit now. So we're saying, okay, the limit of the absolute value, an plus 1 over an, is limit of 2 to the 2n plus 1 over n plus 1. All right. What's this limit going to become? N goes to infinity. So I'm going to say this to you guys. As n gets big, 2 to the n plus 1, which is exponential, goes to infinity. N plus 1 goes to infinity. The numerator goes to infinity faster. So I'm going to say this goes to infinity here. Now 2n plus 1 over n plus 1. Let me show you something in Desmos here. Two raised to the 2x plus 1 power, though. Sorry, I got some Uber Eats coming. Got Uber Eats coming here, so let me give a few minutes here. Hold on. All right. I'm back. I got my Uber Eats. I apologize to you guys for that interruption. Yeah, it doesn't want me to do that here. So now here's what I'm trying to show you. This goes really quick. This increases to infinity really fast. So this limit is infinity, and that's important to know because now we have divergence by the divergence test. Sorry, divergence by the ratio test. All right. Number 10. an, negative 1 to the n, 2 to the n factorial over this product down in the denominator, 3n plus 2. Let's take a look at the an plus 1 term. Negative 1 to the n plus 1 power, 2 to the n plus 1, n plus 1 factorial, 5 times 8 times 11. This product now 3 n plus 1 plus 2. And we'll put that in a bracket here with factorial now. I'm just going to say this by using a little algebra here. We get 3n plus 3 plus 2 factorial, which really gives you 3n plus 5 factorial. So, all right, let's look at the ratio now. An plus 1 over an becomes negative 1 to the n plus 1, 2 to the n plus 1, n plus 1 in factorial over the product of 5 times 8 times 11, all the way up to 3n plus 5 factorial here. We need to see what this looks like in absolute value now. So, once again, using some algebra here, absolute value of negative 1 to the n, negative 1, 2 to the n times 2, n plus 1 times n factorial, using all the tools we've been using here all along. 5 times 8 times 11 up to now we got 3n plus 5. But before that, you had 3n plus the prior term, 3n plus 2. And the next term will be that 3n plus 5 over here. Okay. Now, cancellation. Oops. Sorry about that, folks. It's not true. I'm thinking of my Uber Eats. Thinking of Uber Eats. Let me go back again here. We got to do, before we do some algebra, we have to write down everything that's really there. So I need more space here. We're going to multiply, remember that, multiply by the reciprocal, which is 5 times 8 times 11 up to the 3n plus 2 over negative 1 to the n, 2 to the n factorial now. Okay. Kind of barely fitting that in there. So let's see again how that'll work doing the algebra now, right up here, like we mentioned. All right. Now, so there's more terms now here. Try to get this as close as I can. All righty. So what do we have? 5 times 8 times 11 up to 3n plus 2 over the negative 1 to the n, 2 to the n, and factorial, all in absolute value. So we get to cancel now. This is what I was looking for. 2 to the n. Okay. And factorial, and factorial. Oh. This 5 times 8 times 11 up to 3n plus 2 goes away. So let's be careful and see what we really have now. Okay. Negative 1, 2, n plus 1 in the numerator. And it looks like 3n plus 5 in the denominator. So we have now the absolute value, negative 1 times 2 times n plus 1 over 3n plus 5, which is the absolute value of negative 1 by using properties of absolute value, to n plus 1 over really 3n plus 5. Absolute value of negative 1 is positive 1. And all the terms inside here are positive. So that means we end up with 2n plus 1 over 3n plus 5. So we take the limit now of that absolute value ratio here, ratio test, which is the limit now of, I'll say 2n plus 2 by distributing over 3n plus 5. Okay. Using calculus 1, if you like, we see that this equals 2/3, which is smaller than 1. That's what we are looking for by the ratio test. And that means we have absolute convergence, which really means we have convergence. So absolute convergence implies convergence. So this series converges by the ratio test. Converges by your ratio test. Converges. All right. Now, finally, we're at a really good question, I should say, in some sense. You might say, why is this one a sort of really good question here? because we haven't worked on the root test in a while. And in order to apply the root test, this series has to have b to the n. So this is what I mean by that. Negative 2 to the n really raised to the nth power. This is what you're looking at. This is that b to the n, so we have to use the root test now. So by the root test, we need the absolute value. Remember, the root test looks at this. It looks at the nth root of the absolute value of an. So I need the absolute value of an here. So by properties of absolute value, we end up getting 2 to the n raised to the nth power, because this n term here is positive and the absolute value of 2 is 2. So what we can do now then is we take the nth root of this term, which is really 2 over n, nth root, which we end up getting is really 2 over n. So when you apply the limit of the nth root of the absolute value an, it's the limit of 2 over n. And the limit of 2 over n is 0. That limit that we're looking for is strictly less than 1. Okay, that's what we're looking for. So by the root test, we have absolute convergence, and absolute convergence implies convergence. So I'm going to move this here. So we have convergence here, ladies and gentlemen. This means convergence by the root test. All right. I think I'll try one more. Then I'll get to the Uber Eats. Okay. This is root test as well, because we have a term. Our term is of the form b to the n. This is like the b, if you want to think of it. And you say, what about that 2? Well, I can do some algebra there as well. You're going to see what I'm talking about. So an is negative 2n over n plus 1. That's 2n power. So the absolute value of this term is negative 2n n plus 1 to the 2n power. Now, properties of exponents, what I mean by that is any sort of what? The absolute value of a to the n is this particular product. We got n of these. So by the product rule for absolute values, you end up getting the absolute value of a to the nth power. This is the algebra that I'm referring to with absolute values here. So how does that work with this? Well, that just means you now have the absolute value over here, and this is like the key. Negative 2 to the n over n plus 1. You get to pull out your power is the whole idea here. Okay? That's what I'm saying here by using the properties of absolute value now. So, all right, let's see what this becomes again, by properties of absolute value, I got the absolute value of 2 times the absolute value of n plus 1. All of this is raised to the 2n power. This portion becomes 2, and this portion in the absolute value is strictly positive. Everything there is positive. So you're going to end up with now 2n over n plus 1 now raised to the 2n power here. And that's just the absolute value of an. So when you now apply need another page, the nth root of the absolute value, which is the nth root of 2n over n plus 1. Remember what this really is. This is 2n over n plus 1 now. 2n power, everything raised to the 1 over n power. So you end up with 2n over n plus 1 raised to the second power. So this is the nth root of the absolute value of an. So now, as you take the limit of the nth root, absolute value an, that's the limit of 2n over n plus 1 to the second power. Let's be careful here. Okay. N goes to infinity. So let's see what happens here. As n goes to infinity, 2n over n plus 1 goes to 2. So what that means is 2n over n plus 1 squared will go to 2 squared, which equals 4 here. So this limit is 4. And that 4 limit is bigger than 1. So it's finite, but it's bigger than 1. So this is what we're looking for. If it was under 1, we have absolute convergence. But because that number is bigger than 1, we have divergence. So this is a divergent, ladies and gentlemen, series. So this series diverges, we can say equals infinity, or we can say diverges by, again, the root test. Diverges by the root test. Okay, because we have that nth root. All right, now we got the next one. Yeah, I think the last 3 are going to be root test. Yes, root test. Let's do one more. I got my Uber Eats waiting. Well, okay. Don't know what's going on there. All right. So you say, why is that the root test? Because that's strictly of the form b to the n. So an is n squared plus 1 over 2n squared plus 1 raised to the nth power now. So the absolute value of this term we know by properties of absolute value. We can say a couple of things. We could do it this way and then deduce that this whole thing is positive, which it is, and just say this is really n squared plus 1 over 2n squared plus 1. And don't forget that's raised to the nth power now. Or we could have said that in the first place, that all of this here is positive. So we can get rid of the absolute value. Now, the nth root of the absolute value of an is the nth root of everything we just found right now, which gives you n squared plus 1 over 2n squared plus 1. Now, the limit of this which is the limit of n squared plus 1 over 2n squared plus 1. So this is going to be equal to 1/2, which is smaller than 1 by using calculus 1 if you like. And again, this is what we're looking for, that this is smaller than 1. Okay, this is your finite value of 1/2, smaller than 1. We get convergence. Now, this is convergence here by the root test. Okay. Let's see if we do one more here, ladies and gentlemen. Or maybe I should just get to the Uber Eats. Yeah, I might just get, well, let's try one more. It can't hurt. Again, take a look at this. Nth power. This is going to be b to the n properties of exponents gives you this. This is why this is going to be the root test. So we just have to take the absolute value of an, which is the absolute value of -1, over inverse tangent of n. Okay. Which is the absolute value of -1 over inverse tangent of n raised to the nth power. Properties of absolute value. Meaning the absolute value of a quotient is quotient of absolute values. This whole thing is to the nth power. So you get now, this is 1. You get 1 over inverse tangent is strictly positive for values of n. Okay. Now, the nth root of the absolute value of an is the nth root of 1 over inverse tangent of n to the nth power, which we've seen is really just 1 over the inverse tangent of n. So when you take the limit now of the nth root of the absolute value, well, that's the limit of 1 over the inverse tangent of n. This is as n goes to infinity. Okay. Now, this limit is 1 over, because remember, as n gets big, we know inverse tangent of n goes to pi over 2. So 1 over that inverse tangent of n will go to 2 over pi. And I don't like that ugliness there. Okay. So this limit's going to be 2 over pi. Now remember, pi is approximately 3.14, which means this limit is less than 1, and that's what we're looking for. Our Al value, the limit is 2 over pi, and that number is smaller than 1. So we're going to get convergence, ladies and gentlemen. Absolute convergence implies convergence. So that's what we're looking at. This thing, less than infinity, we get convergence by the root test. All right. Good. So let's do the last one, ladies and gentlemen. I'm doing a big sacrifice. My Uber Eats is here. All right. This is going to be -1 over the natural log of n raised to the n. Again, b to the nth power here. So we lost our connection. We got it back. Thought we got it back. Okay. an is -1 to the natural log of n raised to the nth power, so that the absolute value of an is the absolute value of -1 natural log of n raised to the nth power, which is the absolute value of -1 natural log of n raised to the nth power. Properties of absolute value. This whole thing is raised to the nth power. This is +1, and the natural log of n for natural numbers like 1, 2, and so on is positive. So we got 1 over the natural log of n, whole thing raised to the nth power. This is the absolute value of an. So now when you take a look at the nth root of the absolute value of an, that's the nth root of 1 over the natural log of n raised to the nth, which is 1 over natural log of n. So as we take the limit now of the nth root, absolute value of an, that's the limit of 1 over the natural log of n, and this equals 0. Because your denominator is going to infinity. So 1 over something getting very big is very small. So this is 0, which is less than 1. We're looking for that finite value. And ladies and gentlemen, this is absolute convergence by the root test, which implies you have convergence by the root test. So this is strictly less than infinity, which means you have convergence by the root test. All right, so I get to eat my dinner now, ladies and gentlemen. You guys have heard all that, seen the calling from Uber Eats. And there you go. I'll send this to you guys. I hope you guys enjoyed the demonstration. And have a great evening here. All right, take care.